The night was pitch black and the sea was running heavy swells when HMS Lagan, a British frigate screening the port flank of convoy ONS-18, zigzagged at 18 knots through the North Atlantic darkness on September 19, 1943, at precisely 1:47 in the morning, with Lieutenant Commander Colin Campbell standing on the bridge after 16 continuous hours at sea with burning eyes and exhaustion weighing on him but maintaining the constant alertness that had kept him alive through 3 years of submarine warfare. The convoy consisted of 42 merchant ships heading west from Britain to North America carrying supplies essential to the Allied war effort, and Lagan was one of several escorts hunting German U-boats with sonar equipment that sent out pings and listened for the distinctive echo that would reveal a submarine's position in the dark waters, where visual detection was impossible, and death could come without warning from torpedoes launched by enemies you never saw. Campbell's sonar operator called out a contact with the practiced efficiency that came from months of repetitive training, reporting a bearing of 270 at a range of 2,000 yards and movement from right to left that indicated a probable submarine, information that triggered Campbell's immediate response without hesitation or consultation. Because the procedures for anti-submarine warfare had been drilled into every Royal Navy officer through years of combat experience in the Battle of the Atlantic. Campbell ordered action stations and full speed ahead on a course directly toward the contact while preparing depth charges, and Lagan accelerated to 22 knots with her propellers churning through the water and cavitating in ways that generated tremendous noise that could be heard for miles underwater. But this was entirely acceptable and indeed standard anti-submarine tactics, because you wanted to make noise as you chased the U-boat, forcing it to dive deeper while you closed the range and prepared to drop depth charges that would destroy it, or at least drive it away from the convoy. This approach had worked successfully for 3 years since 1940, when the Royal Navy had developed anti-submarine tactics to something approaching perfection through brutal trial and error that had cost hundreds of ships and thousands of lives, with the basic pattern being that sonar detected submarines, escorts attacked aggressively, and depth charges either destroyed the U-boat or forced it to break off its attack. And while losses remained heavy on both sides, the system fundamentally worked and had prevented Germany from strangling Britain's supply lines despite deploying hundreds of submarines into the Atlantic. Except that on this particular night, something was different in ways that Campbell couldn't yet understand, but would learn in the most terrible way possible, because at 1:49 a.m., just 2 minutes after beginning the attack run, his sonar operator reported something strange that didn't fit any pattern from previous encounters. There was a second contact moving fast at a bearing of 265 and a range of 1,000 yards, closing rapidly at approximately 30 knots. And this made absolutely no sense to Campbell, who understood submarine capabilities thoroughly after years of combat experience, because a second submarine moving at 30 knots underwater was physically impossible, since U-boats had a maximum submerged speed of 7 knots and couldn't possibly match the speed being reported by his sonar operator. Campbell ordered confirmation of the contact and asked for the current bearing, and the sonar operator responded that the bearing was now 264 at 800 yards range, still closing fast, and then added the observation that sent ice through Campbell's veins despite years of experience facing death at sea, stating that whatever this contact was, it was following them, tracking Lagan's course and movements in ways that suggested intent rather than coincidence. The realization hit Campbell with the force of physical impact as he understood that this wasn't a submarine but rather a torpedo, except that it wasn't an ordinary torpedo that traveled in straight lines from launch point to target, but instead something that was maneuvering and tracking and following Lagan's propeller noise in ways that conventional torpedoes simply couldn't do. He had perhaps 20 seconds before impact, maybe less, and his orders came with the desperate urgency of a man who understood he was facing a weapon he'd never encountered before and didn't understand but needed to evade immediately if his ship and crew were to survive the next minute. Campbell ordered hard starboard and all stop with engines cut, hoping that turning sharply and eliminating the propeller noise might cause the torpedo to lose its lock and pass harmlessly by. And the helmsman spun the wheel as ordered while Lagan began her turn. But 22 knots of momentum in several thousand tons of steel doesn't stop instantly, and the frigate continued forward with her propellers still turning and still generating the noise that the torpedo was tracking toward with mechanical precision. The torpedo followed Lagan's turn and adjusted its course to compensate, homing in on the loudest sound in the ocean within detection range, which was Lagan's propellers creating their distinctive acoustic signature as they churned through the water. And at 1:50 a.m. the torpedo struck the frigate's stern just aft of the engine room with a massive explosion, as 1,000 pounds of high explosive detonated against the hull with devastating effect. The stern section, everything aft of the mainmast, simply disintegrated and ceased to exist in any recognizable form as the explosion's force turned steel and machinery and human bodies into fragments scattered across the dark waters, and Lagan's back was broken, leaving her in two pieces with the forward section remaining afloat for approximately 90 seconds before the bulkheads failed under the strain and water rushed in through ruptured compartments, causing the ship to sink bow first as 74 men went into the freezing Atlantic water, where 52 would eventually survive, while 22 were never found, their bodies claimed by the ocean that had already taken so many lives during years of brutal submarine warfare. Lieutenant Commander Campbell was among the survivors, pulled from the water by HMS Lagan, another escort vessel that responded to the distress calls, and he was hypothermic and in shock but alive when he was brought aboard and wrapped in blankets. And the first thing he said while shivering uncontrollably was that the torpedo had followed them, that it had adjusted course and tracked their engines in ways that conventional torpedoes couldn't do. The naval officers listening to Campbell's report thought he might be delirious from hypothermia and confused about what had happened, because everyone knew that torpedoes traveled in straight lines according to basic physics and didn't possess the capability to maneuver or track moving targets after launch. But Campbell insisted on his observations despite their skepticism, and over the next 6 weeks, the Royal Navy would learn through painful and expensive experience that Germany had deployed a revolutionary new weapon that changed the fundamental nature of anti-submarine warfare. The weapon was the acoustic torpedo, designated Zaunkönig or Wren in German military terminology, a torpedo that didn't need to be aimed precisely at launch because it possessed the ability to listen for propeller noise and hunt toward the loudest sound, making it dramatically more effective against escorts that were maneuvering at high speed and generating tremendous acoustic signatures that conventional torpedoes couldn't track, but acoustic torpedoes could follow with deadly precision. The problem of hitting moving targets with torpedoes had plagued naval warfare since the torpedo was invented in 1866 by Robert Whitehead, with early torpedoes being simple devices consisting of compressed air engines and propellers that traveled in straight lines, requiring careful aim and considerable luck to score hits against maneuvering targets that could change course after torpedo launch. By World War II, torpedoes had improved dramatically with better gyroscopes for maintaining course, preset trajectory patterns that allowed complex maneuvers, and spread firing techniques where multiple torpedoes were launched in patterns that increased the probability of at least one weapon hitting the target. But the fundamental limitation remained that torpedoes were essentially blind after launch and couldn't see their targets or adjust course if the target maneuvered, meaning that skilled ship captains who watched for torpedo wakes and turn sharply, could often evade weapons that had been aimed accurately at launch. The solution in theory was obvious, but in practice, extraordinarily difficult, requiring torpedoes to actively track targets after launch by giving them sensors and guidance systems that could detect targets and adjust course to intercept them, regardless of evasive maneuvers. The question was how to provide torpedoes with target detection capabilities when the underwater environment limited most sensing technologies, because vision was impossible since water is opaque beyond approximately 50 feet. Even in ideal conditions, radar wouldn't work underwater due to electromagnetic wave absorption by water, and magnetic detection systems had extremely limited range and could be fooled by various countermeasures or confused by geological features. Sound, however, worked perfectly for underwater detection because water transmits acoustic energy beautifully, with much better propagation characteristics than air, and ships naturally generate tremendous amounts of noise through their propellers and engines and hull vibrations, with a destroyer moving at 20 knots, creating sounds that are audible for miles underwater to sensitive hydrophones. If a torpedo could be equipped with acoustic sensors that heard propeller noise and guidance systems that turned the torpedo toward the loudest sound, then it could track targets effectively and strike with high probability regardless of evasive maneuvers. But while the concept was simple in theory, the execution proved extraordinarily difficult in practice. Germany began research on acoustic torpedoes in 1940 at the Kriegsmarine's Torpedo-Versuchsanstalt, the Torpedo Research Institute located in Eckernförde, with the lead scientist being Dr. Heinrich Drager, who was an acoustic specialist with years of experience studying underwater sound propagation and hydrophone technology and signal processing techniques that would be essential for developing functional acoustic guidance systems. The technical challenges were immense and multifaceted, requiring solutions to problems that pushed the boundaries of 1940s technology in ways that demanded innovative approaches and extensive testing to validate concepts. First, the acoustic sensor had to be sensitive enough to detect propeller noise at reasonable ranges of several thousand meters, while simultaneously not being so sensitive that it picked up the torpedo's own engine noise or the ambient noise of the ocean, or random vibrations from waves and currents, requiring sophisticated filtering techniques to distinguish target signals from background noise. Second, the sensor had to discriminate between different sound signatures, because destroyer propellers sound distinctly different from merchant ship propellers, which sound different from submarine propellers. And the torpedo needed to identify and track the correct target type, rather than being distracted by every noise source in the water. Third, the guidance system had to be simple enough to be reliable and cheap enough to mass produce, because German industry was already stretched to its limits, producing thousands of submarines and millions of shells and mines and other war materials, making complex electronics prohibitively expensive and scarce, requiring Dr. Drager's team to develop mechanical guidance systems that could respond to acoustic signals without requiring sophisticated electronic components. The team worked for 3 years, conducting extensive testing of hydrophones and developing filtering circuits and designing mechanical guidance mechanisms that adjusted torpedo rudders based on acoustic signal direction. And by 1943, they had created a working prototype designated the T5 torpedo with the operational name Zaunkönig, because it listened for its prey like a wren hunting insects through acoustic detection. The technical specifications of the T5 torpedo reflected both the achievements and compromises inherent in developing revolutionary weapons with limited resources, with the weapon measuring 6.2 meters in length and 533 millimeters in diameter to fit standard torpedo tubes, weighing 1,495 kilograms, including a warhead, of 274 kilograms of hexanite explosive, capable of speeds up to 24.5 knots, which was relatively slow compared to conventional torpedoes, but acceptable for attacking escorts, and having a maximum range of 5,700 meters at full speed. The critical innovation was the passive acoustic homing guidance system that used two hydrophones mounted in the torpedo's nose connected to a mechanical servo system that adjusted the rudder based on the direction of detected sound, with the acoustic sensor designed to operate in a narrow frequency band from 200 to 1,200 Hz that corresponded precisely to the frequencies generated by destroyer and frigate propellers at high speed. The frequency selectivity was deliberately designed to make the torpedo ignore merchant ships whose slower propellers generated frequencies outside the targeted range, reflecting the tactical doctrine that escorts should be killed first to leave merchant ships defenseless and vulnerable to conventional torpedoes, representing a strategic approach that recognized escorts as the primary threat to U-boat operations and sought to eliminate them through technological superiority. The first T-5 torpedoes were delivered to U-boat flotillas in August 1943, with strict operational instructions to use them only against escorts and only when the escort was attacking and making high speed with loud propeller noise. And U-boat commanders initially greeted these acoustic torpedoes with skepticism because they sounded like science fiction rather than practical weapons. But orders required their use, and on September 9, 1943, the first T-5 was fired in combat. U-645 under Captain Lieutenant Otto Ferro was pursuing convoy on 2-2, which was well defended by 7 escorts including destroyers and corvettes that were aggressive and well trained. And they had detected U-645 and were actively hunting it with HMS Wanderer, a destroyer, closing at 26 knots while pinging with sonar and preparing to attack with depth charges. Ferro had perhaps 3 minutes before depth charges would start falling around his submarine, and standard procedure would have been to go deep and attempt to evade, while hoping the destroyer's sonar lost contact. But Ferro had a T-5 loaded in one of his torpedo tubes and decided to test the new weapon under actual combat conditions. He fired from a depth of 60 meters at a range of 2,800 meters, while HMS Wanderer was making high speed and generating tremendous propeller noise that made her a perfect target for acoustic homing. And the T-5 ran true with its acoustic sensor activating immediately after launch, detecting Wanderer's propellers and adjusting course to home in on the loudest sound available. Wanderer's lookouts never saw the torpedo wake because acoustic torpedoes approached from unexpected angles rather than straight lines. And at 9:47 a.m., the torpedo struck Wanderer's stern with a massive explosion that broke her back and caused her to sink in 4 minutes, taking 83 crew members with her, while only 37 survived to be pulled from the water by other escorts. The Royal Navy initially attributed Wanderer's loss to a lucky hit from a conventional torpedo fired from an unseen U-boat, not recognizing that they had just witnessed the first successful use of a revolutionary weapon that would change anti-submarine warfare fundamentally. Over the following weeks, more escorts were hit by torpedoes that seemed to track them despite evasive maneuvers, creating growing alarm among naval commanders who recognized that something had changed but didn't yet understand what they were facing or how to counter it. The pattern of losses became impossible to ignore, as experienced escort commanders reported torpedoes that followed their ships through turns and continued tracking even when engines were stopped, suggesting guidance systems that conventional torpedo technology couldn't explain. And by late September 1943, British naval intelligence had accumulated enough reports to conclude that Germany had deployed acoustic homing torpedoes that represented a genuine threat to escort operations. The recognition of this new threat triggered urgent research into countermeasures that could defeat or confuse acoustic guidance systems, with British and American scientists working frantically to develop technologies that would restore the tactical balance before losses became unsustainable. The most effective countermeasure proved to be remarkably simple in concept, though requiring careful engineering to implement effectively, consisting of a noise-making device towed behind escorts that generated louder sounds than the ship's own propellers, causing acoustic torpedoes to track toward the decoy rather than the ship itself. The device was designated Foxer in British service and consisted of two serrated metal bars that clattered together when towed through water, creating tremendous noise in exactly the frequency range that T5 torpedoes were designed to detect. And when properly deployed, the Foxer caused acoustic torpedoes to explode harmlessly behind the escort, rather than striking the hull. Foxer deployment began in October 1943 and spread rapidly throughout escort forces, dramatically reducing the effectiveness of German acoustic torpedoes almost overnight, as U-boat commanders discovered that their revolutionary weapons were suddenly detonating behind targets rather than striking them, creating confusion and frustration as the technological advantage they had enjoyed for barely 6 weeks evaporated through Allied countermeasures. The acoustic torpedo arms race had begun in earnest, with Germany attempting to develop improved versions that could discriminate between propeller noise and decoy noise, while the Allies continuously refined their countermeasures and developed their own acoustic weapons that would ultimately prove far more successful than the German originals. The American response to German acoustic torpedoes went beyond simple defensive countermeasures to include development of their own acoustic homing weapon, specifically designed for anti-submarine warfare, designated Mark 24, though it was actually a torpedo designed to be dropped from aircraft and called Fido in operational use, representing a technological leap that transformed the nature of aerial anti-submarine operations. The Mark 24 was designed to be deployed from patrol aircraft that had detected submarines through visual observation or radar or sonar buoys, dropped into the water near the submarine's estimated position, where it would sink to activation depth and begin listening for propeller noise with sophisticated hydrophones that were more sensitive than those used in German T5 torpedoes. The brilliance of the Mark 24 design was that it operated at slower speeds than conventional torpedoes, making it much quieter and allowing its acoustic sensors to hear submarine propellers more clearly without interference from the torpedo's own engine noise, and it was specifically optimized for detecting the relatively quiet electric motors used by submerged submarines rather than the loud propellers of surface ships, making it ideal for the anti-submarine role. Mark 24 entered service in March 1943, and by the end of the war had sunk 37 German U-boats and 18 Japanese submarines, achieving an extraordinarily high success rate of nearly 50%, where approximately half of all Fidos dropped resulted in confirmed kills, dramatically exceeding the effectiveness of conventional depth charges or rockets. The irony was profound because the acoustic torpedo that Germany had designed to kill escorts ended up being most successful when America used the same basic technology to kill submarines, demonstrating that revolutionary weapons can be turned against their creators when opponents develop countermeasures and adaptations faster than the original innovators can respond. By late 1944, Germany had developed the T-11, an even more sophisticated acoustic torpedo that used active sonar rather than passive listening, sending out sound pulses and detecting echoes to track targets, even if they were running silent, representing a technological advance that anticipated modern torpedo guidance systems, but came too late and in too small quantities to affect the war's outcome. The T-11 was extraordinarily sophisticated for its era, but also too expensive and complex to manufacture in quantity, given Germany's deteriorating industrial situation, with only a handful produced before the war ended in May 1945. Though the concept proved sound, and after the war, every navy copied the active sonar guidance approach, leading to modern torpedoes like the Mark 48, Spearfish, and Type 65, that all use active sonar guidance as descendants of Germany's final acoustic torpedo development. The technology that Germany pioneered in 1943 with acoustic homing is now universal across all torpedo designs, with passive and active acoustic guidance considered standard features rather than revolutionary innovations, demonstrating that Germany was right about the potential of acoustic torpedoes, but deployed them too early before the technology had matured, and before they could be mass-produced reliably. If Germany had waited and developed the T-11 in 1942 instead of 1944, and produced 5,000 units instead of 50, the Battle of the Atlantic might have ended very differently, with escort losses becoming unsustainable and merchant shipping losses climbing beyond Britain's ability to replace them. But the historical reality was that Germany introduced acoustic torpedoes with insufficient testing and inadequate production capacity, and without anticipating countermeasures, resulting in a brief period of tactical advantage that lasted approximately 3 months before Allied countermeasures negated the weapon's effectiveness. The statistics tell a sobering story about the limited impact of Germany's acoustic torpedo program despite its revolutionary technology, with approximately 640 German acoustic torpedoes fired during the war, resulting in 53 Allied ships hit and only 19 ships sunk, producing a success rate of just 8.3% compared to conventional torpedoes that achieved approximately 12% success rates, meaning the revolutionary weapon was actually less effective than the conventional weapons it was supposed to replace. The reasons for this disappointing performance included the rapid deployment of Foxer decoys that confused acoustic guidance systems, changes in escort tactics that reduced propeller noise when possible, and Germany's inability to produce acoustic torpedoes in sufficient quantities to overwhelm Allied defenses before countermeasures became widespread. The window of opportunity for German acoustic torpedoes lasted from September to December 1943, a period of approximately 90 days during which they changed naval warfare forever, by proving that acoustic guidance worked and demonstrating its potential and terrifying Allied navies into developing their own versions. But then the advantage disappeared forever as countermeasures and tactics evolved faster than Germany could adapt. The acoustic torpedo paradox represents one of the great ironies of World War II technology, because Germany developed the weapon and used it against Allied escorts, sinking 19 ships and killing thousands of sailors. But then the Allies copied the technology and used it against German submarines, sinking 55 submarines and killing thousands of German sailors, demonstrating that revolutionary weapons can be turned against their creators when opponents adapt faster and learn from the technology. This pattern of innovation followed by counter-innovation repeated throughout World War II, across technologies including radar, sonar, proximity fuses, jet engines, and guided missiles, with every technological leap triggering a counter-leap, and every advantage becoming a vulnerability when opponents developed countermeasures, proving that victory goes not to the side with better technology alone, but rather to the side that adapts faster and learns from technology and counters it and copies it and improves it more effectively than their enemy. Germany's acoustic torpedo experience demonstrated this principle clearly, because brilliant German engineers created a masterpiece weapon that was revolutionary and ahead of its time. But strategic thinking failed by deploying the weapon in insufficient quantities, without adequate testing, and without anticipating countermeasures. assuming incorrectly that technological superiority alone would be enough to ensure success. The lesson was that technology alone never wins wars, but rather the ability to adapt and learn and iterate and turn enemy innovations against them determines outcomes. And the acoustic torpedo proved this in the most brutal way possible, through the loss of ships and submarines and thousands of lives on both sides as the weapons technology race accelerated through the final years of the war. The technical sophistication of the T5 acoustic guidance system deserves deeper examination, because it represented a remarkable achievement in electromechanical engineering given the technological limitations of the early 1940s when electronic components were primitive by modern standards, and computing power essentially didn't exist outside of specialized code-breaking machines. The hydrophones mounted in the torpedo's nose consisted of piezoelectric crystals that converted acoustic pressure waves into electrical signals, with the crystals carefully selected and calibrated to be most sensitive in the 200 to 1,200 Hz frequency range, where destroyer propellers generated their strongest acoustic signatures, while being relatively insensitive to frequencies outside this range that might include ocean ambient noise or the torpedo's own propulsion sounds. The two hydrophones were positioned on opposite sides of the torpedo nose at specific angles that allowed the guidance system to determine the direction from which sounds were arriving through amplitude comparison, with the hydrophone facing the loudest sound receiving stronger signals than the hydrophone facing away. And this amplitude difference was translated by the mechanical servo system into rudder commands that turned the torpedo toward the source of maximum noise. The servo mechanism itself was an elegant piece of mechanical engineering consisting of springs and levers and differential gears that physically moved the torpedo's rudder in proportion to the signal strength difference between the two hydrophones, requiring no electronic amplifiers or computing components, but rather relying entirely on mechanical force transmission from the acoustic sensors to the control surfaces. The filtering circuits that prevented the torpedo from tracking its own engine noise or being distracted by ambient ocean sounds represented perhaps the most challenging aspect of the design, because they had to discriminate between very similar acoustic signatures in real time while operating reliably in the harsh underwater environment where temperature gradients and pressure changes and saltwater corrosion all conspired to degrade performance. The Draeger's team developed passive filters using combinations of capacitors and inductors tuned to specific frequency ranges, creating bandpass characteristics that emphasized target frequencies while attenuating unwanted noise. Though the limitations of passive filtering meant that the system occasionally locked onto incorrect sounds and sent torpedoes chasing false targets or losing tracking entirely when acoustic conditions changed unexpectedly. The operational procedures for firing T5 torpedoes reflected both the weapon's capabilities and its limitations, with U-boat commanders receiving detailed instructions that emphasized waiting until escorts were making high speed and generating maximum propeller noise before launching, typically during the escort's attack run when the destroyer or frigate would be charging toward the U-boat's position at 20+ knots with propellers cavitating loudly. The firing solution calculations were simpler than for conventional torpedoes because precise aim was less critical when the weapon could guide itself after launch, though commanders still needed to ensure the target was within the torpedo's detection range and generating sufficient acoustic signature to activate the guidance system effectively. The psychological impact on escort crews who survived acoustic torpedo attacks was profound and lasting because the experience of being hunted by a weapon that could follow evasive maneuvers created a sense of helplessness that conventional torpedo attacks didn't produce, with survivors reporting dreams and flashbacks of hearing the torpedoes approach and feeling powerless to escape as it tracked their every maneuver with mechanical precision. The knowledge that standard evasion tactics were ineffective against acoustic torpedoes forced escort commanders to develop entirely new approaches to submarine hunting that emphasized reducing propeller noise whenever possible and maintaining readiness to deploy Fokker decoys at the first indication of torpedo launch. The development and deployment of Fokker decoys represented an impressive achievement in rapid countermeasure engineering, accomplished in approximately 6 weeks from first recognition of the acoustic torpedo threat to widespread deployment of effective countermeasures throughout escort forces operating in the Atlantic. The Fokker design went through several iterations as engineers refined the acoustic signature to match the frequencies that T5 torpedoes tracked most effectively, with early versions sometimes failing to distract torpedoes because their noise spectrum didn't precisely match propeller frequencies. But by late October 1943, the improved Fokker design was reliably causing acoustic torpedoes to detonate harmlessly in the wake of towing ships. The tactical drawbacks of Fokker deployment included reduced speed for ships towing the devices because the drag created by the noisemaker reduced maximum speed by several knots, forcing escort commanders to choose between acoustic torpedo protection and high-speed maneuverability that was essential for depth charge attacks, creating difficult tactical decisions about when to deploy or retrieve Fokker based on threat assessment and operational requirements. Additionally, the tremendous noise generated by Fokker interfered with the towing ship's own sonar capabilities, making submarine detection more difficult while the decoy was deployed and creating periods of acoustic blindness that submarines could potentially exploit for attacks or escapes. The German response to Fokker countermeasures involved attempts to modify T5 guidance systems to discriminate between propeller noise and decoy noise through frequency analysis and amplitude patterns, recognizing that Fokker devices generated different acoustic signatures than actual propellers, despite operating in similar frequency ranges. But these discrimination improvements proved difficult to implement reliably and never achieved the level of effectiveness that would restore the acoustic torpedo's original advantage. The T5A variant, introduced in early 1944, included improved discrimination capabilities and was somewhat more resistant to Fokker countermeasures, achieving modestly better success rates than the original T5 design, though still falling far short of the devastating effectiveness that had characterized the first weeks of acoustic torpedo deployment. The naval intelligence aspect of the acoustic torpedo story reveals how signals intelligence contributed to understanding and countering the new threat, with Bletchley Park decrypts of German naval communications providing crucial information about T5 operational characteristics and deployment patterns and effectiveness assessments that allowed Allied naval commanders to develop appropriate countermeasures and tactics more rapidly than would have been possible through combat experience alone. The intercepted German messages revealed the Kriegsmarine's frustration with declining T5 effectiveness after Fokker deployment, and their debates about whether to continue using acoustic torpedoes or revert to conventional weapons. Intelligence that confirmed the Allied countermeasures were working and justified continued investment in acoustic defense technologies. The American Mark 24 Fido represented a fundamentally different approach to acoustic torpedo design compared to the German T5, optimized for the specific requirements of air-launched anti-submarine weapons rather than being adapted from existing torpedo designs. And this purpose-built approach resulted in superior performance characteristics that made Fido far more effective than T5, despite using similar basic principles of acoustic guidance. The key differences included Fido's much slower speed of approximately 12 knots compared to T5's 24 knots, which made Fido quieter and allowed its hydrophones to hear submarine propellers more clearly, without interference from the weapon's own propulsion noise, creating better signal-to-noise ratios that improved tracking reliability. Additionally, FIDO's acoustic sensors were specifically tuned to detect the relatively quiet electric motors used by submerged submarines rather than the loud propellers of surface ships, requiring different frequency response characteristics and greater sensitivity than T5's design. And the American engineers developed more sophisticated filtering circuits that could distinguish submarine signatures from ocean ambient noise with greater reliability than German passive filters achieved. The deployment method for FIDO also differed fundamentally from T5, because aircraft could position the weapon more precisely near suspected submarine locations using visual observations or sonar buoy data, eliminating the long-range detection requirements that complicated T5 operations and allowing FIDO to activate its guidance system in relatively close proximity to targets where acoustic detection was easier. The success rate statistics for Mark 24 FIDO dramatically exceeded those of German T5 torpedoes because approximately 50% of FIDOs dropped resulted in confirmed submarine kills compared to T5's 8% success rate, demonstrating that purpose-built design optimized for specific missions outperformed adapted designs that attempted to serve multiple roles, and also reflecting the fundamental difference between attacking submarines that were operating at limited speeds and generating minimal noise versus attacking escorts that were operating at high speeds and generating tremendous acoustic signatures. The psychological impact of FIDO on German submarine crews who survived attacks was severe because the weapon could strike from above without warning when submarines thought they were safe at depth, and the knowledge that aircraft carried weapons that could hunt submarines autonomously through acoustic detection created constant anxiety during patrol operations. The evolution of submarine tactics in response to acoustic torpedo threats from both sides demonstrated the continuous adaptation cycle that characterized World War II's naval warfare, with submarines learning to minimize acoustic signatures by running on electric motors at reduced speeds when threatened, though this reduced mobility made them more vulnerable to depth charge attacks and limited their ability to pursue convoys effectively. U-boat commanders developed procedures for detecting Foxer deployment through hydrophone monitoring, listening for the characteristic clattering noise that indicated escorts had activated their acoustic decoys. Though this information provided limited tactical advantage, since the Foxer's presence meant attacking with acoustic torpedoes would be ineffective regardless of whether the U-boat knew the decoy was deployed. The technical limitations of 1940s acoustic guidance systems included susceptibility to thermal layers in the ocean that could refract sound waves and create acoustic shadows, where torpedoes lost contact with targets, vulnerability to high ambient noise levels from weather or wave action that could mask propeller signatures, and inability to discriminate between multiple targets in close proximity, causing torpedoes to sometimes track the wrong ship or become confused and circle aimlessly when multiple acoustic signatures competed for the guidance system's attention. These limitations were well understood by German engineers who attempted to address them through improved hydrophone designs and better filtering circuits. But the fundamental constraints of passive acoustic detection meant that some environmental conditions would always degrade performance regardless of engineering refinements. The strategic implications of acoustic torpedo deployment extended beyond the tactical effectiveness of individual weapons to include broader effects on convoy operations and escort tactics that influenced Allied shipping losses and submarine kill rates throughout 1943 and 1944. The initial period of acoustic torpedo advantage in September and October 1943 forced escorts to operate more cautiously and maintain greater distances from suspected submarine contacts, reducing the aggressiveness of anti-submarine operations and allowing some U-boats to escape attacks that might otherwise have destroyed them, contributing to a temporary increase in merchant shipping losses during this period. However, Once Fokker deployment became widespread, and escort crews gained confidence in their countermeasures, operations returned to previous levels of aggressiveness, with escorts closing rapidly on submarine contacts without fear of acoustic torpedo retaliation. The production statistics for German acoustic torpedoes revealed the industrial limitations that prevented Germany from fully exploiting their technological advantage, with total T5 production reaching approximately 640 units compared to the tens of thousands of conventional torpedoes manufactured during the war, reflecting both the greater complexity and cost of acoustic torpedoes and the competing demands on German industrial capacity from other weapons programs. This limited production meant that U-boats typically carried only 2 or 3 acoustic torpedoes among their standard load of 12 to 14 torpedoes total, requiring commanders to conserve acoustic weapons for high-value targets or situations where conventional torpedoes were unlikely to succeed. And this conservation instinct sometimes led to missed opportunities where acoustic torpedoes might have achieved significant results if used more liberally. The post-war analysis of acoustic torpedo effectiveness conducted by naval historians and weapons analysts revealed several important lessons about technology deployment and countermeasure development that influenced subsequent weapons programs during the Cold War era, with particular emphasis on the importance of adequate testing before operational deployment, the necessity of anticipating countermeasures and developing countermeasures before weapons are fielded, and the value of maintaining production capacity sufficient to overwhelm enemy defenses through sheer numbers when countermeasures inevitably appear. The German experience demonstrated that revolutionary weapons introduced in small quantities can be rapidly countered and neutralized before they achieve strategic impact, while weapons introduced in large quantities can maintain effectiveness longer by forcing enemies to develop, produce, and deploy countermeasures across their entire force structure before the threat is adequately addressed. The legacy of World War II acoustic torpedoes extends directly into modern naval warfare, where every submarine-launched torpedo and every air-dropped anti-submarine weapon uses some form of acoustic guidance as a standard feature rather than experimental technology, with contemporary systems employing both passive listening for target-generated noise and active sonar that sends pulses and listens for echoes, providing redundant guidance modes that ensure weapons can track targets under various environmental conditions and operational circumstances. The Mark 48 torpedo used by the United States Navy represents the direct descendant of both the German T5 and the American Mark 24, combining the best features of both weapons with 70 years of subsequent engineering refinement and incorporating sophisticated signal processing algorithms that run on embedded computers to discriminate targets from countermeasures and optimize tracking in complex acoustic environments. The human cost of the acoustic torpedo innovation and counter-innovation cycle included thousands of sailors and submariners, killed on both sides as weapons and countermeasures evolved through brutal trial and error, with each technological advance purchased through lives lost in combat testing under operational conditions where failure meant death for crews who had no opportunity to benefit from lessons learned through their sacrifice. The 19 Allied ships sunk by German acoustic torpedoes represented not just statistical losses, but rather individual tragedies where hundreds of sailors died in explosions and drownings while their shipmates watched helplessly, creating traumatic memories that survivors carried for the rest of their lives, while the 55 submarines sunk by Allied acoustic weapons took thousands of German submariners to their deaths in the crushing depths where submarine hulls imploded under pressure or slowly flooded, while trapped crews suffocated in darkness. The ethical dimensions of acoustic torpedo development included questions about whether revolutionary weapons that increase lethality without providing targets any opportunity for defense represented progress or merely escalation in the destructiveness of warfare, though these philosophical considerations had little impact on weapons programs driven by military necessity and national survival imperatives, where any advantage over enemies justified development and deployment regardless of broader humanitarian concerns. The post-war reflection on acoustic torpedo history by veterans and historians emphasized both the remarkable engineering achievements represented by functional acoustic guidance systems built with 1940s technology and the sobering reality that these achievements serve primarily to kill people more efficiently, creating a complex legacy where technical admiration mingles uncomfortably with recognition of the human costs involved in advancing weapons technology. The acoustic torpedo story concludes with recognition that Germany's revolutionary weapon changed naval warfare fundamentally by proving acoustic guidance was practical and demonstrating its potential effectiveness, forcing all naval powers to develop similar capabilities and establishing acoustic homing as the dominant guidance method for torpedoes that continues to the present day, though the German implementation came too late and in too small quantities to affect World War II's outcome significantly, serving primarily to accelerate development of Allied acoustic weapons that ultimately proved more effective than the German originals and contributed to the defeat of the U-boat campaign that the acoustic torpedo was supposed to salvage.